All right, in 8.2a, we're going to look at confidence intervals for proportions and how do we actually create one. So what are the three conditions for constructing a confidence interval for a proportion, and what happens if one of the conditions is violated? So the first one is it has to be a random sample. It has to come from a well-designed sample or an experiment, right? The second condition is that independence condition that we've talked about before, where the sample has to be less than or equal to 1/10 the size of the population. The third condition is what we call the large counts condition, and we talked about this in our previous chapter, where we check to see if the sampling distribution is approximately normal. Now, what's different here is in the previous chapter we used p right here instead of p hat. But here's the deal. If we're estimating the parameter, that means we don't know the parameter. All we have to use is the p hat, the statistic from our sample. That's the best we can do when we're doing a confidence interval. So when you do large counts, you're going to use p hat when doing a confidence interval. So if any of these are violated, the actual capture percentage will be different than advertised. Like if you're trying to be 95% confident, but one of these is off, then you probably are only about 90% confident or even less. So that's what's going to happen if they fail one of these. You can still create the interval, it's just not as good as it's supposed to be. So when the standard deviation of a statistic is estimated from the data, the result is called the standard error of the statistic. What's the difference then between the standard deviation of the statistic and the standard error? Well, the standard deviation of the statistic is sigma. The standard error is SE. Now, what does that look like? Well, both of them measure the typical distance from the mean, but the sigma is when you know the parameter p from the population. And the standard error is when all you know is the p hat value. Okay? So when you're doing a confidence interval, we have to depend on the standard error. We don't really know sigma because we don't know the parameter p. They kind of go hand in hand. So if I don't know sigma, my next best option is the standard error. So what's the formula? Well, the formula for standard error looks a lot like the formula for standard deviation. It's, instead of using p, we use p hat. So same song, second verse. We don't know p. That's what we're trying to estimate. So we only have the proportion from our sample. That's the only thing we can use to be our best guess on standard error. Now the next part of a confidence interval that you need to know is a critical value. How's it calculated and why is there a star in it? Well, the critical value when we do proportions is called ZStar. And remember the confidence interval formula that we have, it starts with the statistic, our point estimate, the add or subtract, then the product back here of ZStar times our standard error. Well, I just gave you the formula for standard error, but then what about the ZStar part? Well, what does it do? It measures how many standard errors we need to extend the interval to the desired confidence level. It's basically a big determinant in the length of our arms of margin of error. It reminds us also that it isn't a normal z-score. That's why we have the star. We find the z-star by using an inverse norm function, or you could use a z-table, but the inverse norm function in your calculator is how I'm going to demonstrate for you in the slides. So let me show you what I mean. Find the critical value for a 96% confidence interval for a proportion. Alright, so what you have to do is visualize the curve. And I want the middle 96%. That's my confidence level. And if the middle is 96, that means there's 4% left out there. And it's split evenly between the two tails. There's 2% here, 2% over here. So then what I have to do is find the z-score that cuts this area off right here. I could also find the same one here, but what you're going to notice is that they're the same number. This one's negative, this one's positive. So in my calculator, I'm going to go to the inverse norm menu, and it looks like this. It's going to ask you for area, mu, and sigma. The area is the area in the tail that you figure out when you draw your picture. So my area is 0.02. Mu is always going to be 0, and sigma is always going to be 1 when you're doing this, because it's a standardized score. And in my calculators, it does ask for which tail. Well, I'm going to default to left tail because that's where calculators default if they don't have that option. So it's always this left tail. So when I press calculate, this is the output it gives me. And it gives me a negative 2.053 or 54. Notice it's negative, and it should be negative. The left side would be negative. If I had put in here in my area the 0.98, representing the cutoff of the highest 2%, that would give me a positive 2.054. All right, so they're mirror images. And really, it doesn't matter what you get right here as far as the sign, because if you look back at the equation, it has a positive and a negative, and it's coming from that z-score. It's going to get factored in. So here's the formula for the one sample interval for a proportion. It looks like this. Remember, we start with our point estimate, p hat. We add and subtract z-star, our critical value, and this is the standard error of the statistic. Now, is it on the formula sheet? Well, not exactly. On the formula sheet, it looks like this. It's very, very generic because you're going to use these values for proportions, and in future videos I'm going to show you what you're going to use for means. But the idea is the same. You always start with the statistic, the critical value, and then the standard error of that statistic. Okay? Now, this formula is on your sheet in the different pieces, like the standard error of a statistic is on the formula chart. That's there for you, and I've shown you how to find critical value, and statistic should be given to you. All right, I'm going to slowly walk you through an example of how all this works together. All right, students in an AP Stats class want to estimate the proportion of pennies in circulation that are more than 10 years old. So to do this, they collected a random sample of pennies. Overall, 57 of the 102 pennies they have are more than 10 years old. So as I walk through this, I want you to notice the 4-step process because you're going to be expected to use it as we go along, and we'll develop it more in the next video. So part A says to state. What that means is to identify the goal, the population, and the parameter of interest. So what would that look like? Well, the goal here is that we want to estimate the true proportion of pennies more than 10 years old that are still in circulation. All right, there's a lot of context in here, and I'm talking about the population here, the true proportion of all pennies. The second step is to plan. And when you're asked to plan, it's a lot of steps. You have to name the test we're using and check the conditions. So the first thing you need to know, the test we're going to do is a 1 proportion z interval. And then the conditions we've talked about. First, random. Was our sample random? Well, it tells us that it's a random sample of 102 pennies, so that condition is satisfied. 10%. We can assume that there are more than 10 times 102, which 1,002 pennies in the U.S. circulation. We know that for a fact. It's safe to assume that. So the third condition is the large counts. But to do large counts, I need to know what p hat is. So I'm going to read my story again and find what p hat is. So p hat is 57 divided by the 102, the proportion of the pennies out of my sample that were more than 10 years old. So I divide it to get 0.559. That's the p hat. Now to calculate my large counts, remember, I have to do the sample size times my p hat has to be greater than or equal to 10. So if I plug in my values, I get 57.02. That's greater than 10. It works. And then n minus the complement of that times our sample size, again, here it is, gives me 44.98. Both are greater than 10, so it passes large counts. I can then proceed using a confidence interval equation. Now the large counts justify the sampling distribution being approximately normal, which allows me to use the z-scores and the z values. All right, the third step is the do step, okay? To construct a 99% confidence interval for the parameter. So remember our formula right here. P hat plus or minus C star times standard error of P hat. So I need to find, I found P hat already. Z star is my next thing I need to find. So to find Z star, I need to sketch my graph out and think about this. So if 99% confidence is in the center, that means I have 1% left in the tail. So if I split that 1%, it's 0.5%. I convert that percent to a decimal, 0.005, and I'm going to use the inverse norm function in my calculator. I'm going to put in the area of 0.005, 0 for mean, 1 for standard deviation, and using the left tail. And it gives me a Z star value of 2.578. So now I can plug in the stuff I know in my equation. I know my p hat, I know my z-star, and there's my p hat, 1 minus p hat over n, take the square root, all this business. I'm showing my work and continuing to solve it, continuing on, and there's my confidence interval. At this point, I take the 0.559 and I subtract 0.126 and I get this. Then I start at 0.559 again and I add 0.126 and I get this value. Now this is all the work I need to show. That is all the steps in there. Now to conclude, I need to interpret the interval in context. We are 99% confident that the true proportion of pennies more than 10 years old that are in circulation is between 0.433 and 0.685. Part E says, is it plausible that more than 60% in circulation are more than 10 years old? So you go back and you look at your interval. Is more than 60% in there? Well, yeah, 60% is definitely in there, and there's more than 60%. So it is possible. We don't know for sure, but it isn't within the range of possible values. So you say, yeah, because 0.60 is within the interval, it is a plausible value for P.